Good morning. My name is Ashutosh Garg. I work as a solution provider with Furnace Improvements. In March this year, our company completed 25 years in business in the US. Furnace Improvements is conducting free fired heater training webinars this year as a part of our Silver Jubilee celebrations. Welcome to today's training session on ethylene cracking furnaces. I welcome you all. We have received more than 50 registrations today, and we thank all of you for your time and interest. So first, why are we talking about ethylene cracking furnaces? We don't build ethylene crackers. We can help you improve the performance of your cracking furnaces. All furnaces are the same. Ethylene cracking, the only difference is it has a radiant coil where the reaction is taking place. It is a very high temperature furnace. Other than that, the furnace, like any other furnace, has a radiant section, convection section, burner, stack, waste heat recovery, ID fan. They are all designed and built to the same standard. So we think we can help you improve the run length and coil life of your furnaces. Today, we will talk briefly about our coking index and our inclined firing that can be used in your furnaces. We will have the interactive presentation for 90 minutes. Please keep on sending your questions on the GoToWebinar platform. We had done the session 1 in May this year. All the previous webinars are available on our YouTube channel. So let me start the Kahoot. We will be conducting this webinar through Kahoot. It's a game-based learning platform that makes learning awesome. I discovered this platform while I was playing a trivia with a bunch of my friends. And I was so impressed by the platform that I decided to do all our webinars using this interactive platform. I think it's a thing which is interactive. I mean, I have been doing training for almost 25 years. And most of the training which I have done in the past, whether it was for engineers or whether it was for operators, was mostly a one-way transaction. I would get some feedback during the engineers class, but most of the time it was one-way traffic. So what I find this platform to be different is that you can interact, and interact is the key. We are talking about two-way street, back and forth. And that's what I appreciate or admire about this platform. So, and this is completely secure. I think it is used by more than 400 of the biggest corporations in US, including Microsoft, Google, and Apple. So it's a very secure platform. Your identity is completely anonymous, and you will really enjoy this game. So as I said, this is basically for two-way platform. That's what we will do. The pin is 1576463. If you have not registered, again, I request you to register. And you can go to www.kahoot.it or download the app on your phone. It's both available both on Apple and Android platforms. So I've always started my training sessions with a brief introduction of myself, even though I think sometimes I don't even need an introduction. I'm a chemical engineer. I've been working on furnaces for almost more than 45 years. I passed out of IIT Kanpur in 1974. And since 1976, I've been working on fired heaters and combustion systems. I've worked in KT India, Engineers India, and KTI Corporation in US. I've been working on with furnace improvement since 1996. We work on revamping fired heaters and improving this thing. This presentation today, my team has worked very hard. I'm only the face, the front face, but it is my team members, Sushil, Meghna, Deepika, and all the process people who have been working hard on all these webinars. And they basically, including the designers and 3D people who develop all these sketches. So I want to thank all my team members who have contributed to the webinar. So furnace improvements pays our bills. So I have to give you a little bit commercial or web infomercial on furnace improvements. Let me tell you a story how I started furnace improvements. It was 1994 or so. I was taking a tour of Baytown and Texas City here in Houston with a sales engineer from KTI. And I just asked Bob, I said, Bob, there are furnaces all around. Who takes care of these furnaces? He said, nobody. And I said, why? He said, fixing furnaces is a dirty business. All furnace vendors, they want to work on new heaters. So our focus has always been working on new heaters. So as luck would have it, there was an opportunity in 1996. I got laid off, not exactly laid off, but I got an opportunity in 1996 to start. And I said, why don't I take up this challenge of working with old furnaces, fixing old furnaces? And that's what we have been doing since 1996. It's been almost 25 years. And we have been very lucky. I mean, our clients have been extremely gracious, I would say, and have promoted us, have given us a lot of business. So today we have 3 offices. Our main office is in Noida, India. We opened it in 2005, and that's where all the engineering talent resides, actually. The Sugarland office, which used to be a big office, is now a project office or sales office. It only has 5 people. And then we opened a CFD office in Pune in 2014 because we found CFD is a very powerful tool. And we can demonstrate to the clients if CFD is done correctly, the value of our improvements. We can show it to you how inclined firing or whatever we are proposing on burners or heaters, you can see it. So that's typically what we focus on, what we have been working. We provide unique solutions. So one of the things I want to tell you is We have a contrarian approach. We always challenge the things the way they have been done. We say, why not do it differently? And that has been our motivation all these 25 years. Why not do something new? Why not? And we have been very successful. We have 3 patents. We have split flow, we have inclined firing, we have smart damper. So we have been trying to resolve problems. We take pride in doing high quality technical work. My team is very, very good. They do all this. Because of time difference, we practically can work around the schedule, around the clock. And we keep schedules. Our philosophy is do it once, do it right. I want to tell you a story. There was a refinery in Latin America, Suriname. I don't know how many of you have heard of Suriname. It is a Dutch colony, and they even have a refinery, and they were upgrading their refinery. They wanted to buy, they bought 9 heaters, but in reality, they ordered only 8 heaters, and they forgot the 9th heater. And later on, they went through whole of USA. They contacted all the people, heater vendors, and nobody could supply them a heater in 4 months. We took up the challenge and we made sure that heater is on the ship within 4 months. That is how fast our team works. It's because we are focused, we are small, we can perform. So let's talk about, we plan to do 4 sessions on ethylene crackers. This is our second session. We organize the first session in May. They are at 3 months interval. If you have missed my first session, you can see it on GoToWebinar or on our YouTube channel. We talked about basic introduction, talked about nomenclature, fuels and combustion, and reaction kinetics. That's what we talked about in our first session. So today we will talk about radiant section, which is the main section in any furnace. We'll talk about how it is designed, what are the main components, talk a little bit about coil metallurgy and transfer line exchangers. Then we will move to convection section. And then finally, stack, draft, and ID fan. That's what we will be covering today. So let's talk about a little bit about ethylene cracking furnace. As I said in the beginning, there are 3 types of heaters. The first type of heater is the simplest heater, which is called a gas heater or a liquid heater, whereas the liquid goes in, liquid comes out, or gas goes in, gas comes out. The second type of heater is where a phase change occurs. That means liquid comes in, but liquid plus gas goes out. They are very common in refineries. We are talking of crude, we are talking of vacuum, cokers, all these type of things. The third type of heater is where a reaction is taking place. That means whatever is going inside is not the same what comes out. And these are called reaction heaters. You can call coker as a mild reaction heater because it's a coke which comes out of the coker heater. Other 3 heaters basically are EDC cracking heaters, which are used for manufacture of PVC. We talk about steam methane reformers for making hydrogen, making ammonia, making methanol. That's another reaction heater. And then the ethylene crackers. So these are called as tubular heaters, tubular reactors. In all these cases, we are talking of endothermic reactions. We're talking of endothermic reactions, and we have to supply heat, and that is why we use a furnace to supply that heat. What we do, we take the feed, we preheat, we preheat in the convection section, then we add dilution steam, and then again we preheat in the convection section. If we have a gaseous feed, then we are only talking of sensible energy. And if we have a liquid feed, then we also need latent heat. We'll talk about energy conservation, but one of the differences I find between a refinery and a petrochemical plant is petrochemical business is very competitive. It is so competitive that people are talking about maybe 99%, or whether you can get it or not, but they are talking of 95, 96, 97% efficiency improvement, efficiency of the furnace. And at the same time, I see refinery furnaces, they are both side by side. But the refinery furnaces are working on 60%, 70%, 75% efficiency. And it's happening side by side in the same country, but that's basically the nature of business. So I think it is good in the sense that we are talking of greenhouse gases, carbon-free world, and the more efficiency we talk about, the less emissions we will have. And my thinking is all these furnaces will see a lot of change in the next 20, 25 years. I'm not even sure how many furnaces will even survive, but maybe they all start firing hydrogen actually. I don't know. I'm just thinking, maybe they will start firing hydrogen. They are already, has been in the news for NOx emissions for the last 25 years, and now maybe it's a greenhouse gases, what we will talk about. So this sketch shows a principal arrangement of cracking furnace. We're talking of a radiant section, convection section, transfer line exchangers, and ID fan on the top, stack and ID fan in the top. No matter whose furnace you got, whether you got Lummus furnace or whether you got Kellogg furnace or you got Technip or you got Stone Webster, Linde, radiant section more or less remains the same. Maybe the coil is different, but other than that, the radiant section remains the same. The convection section is mostly very similar. Transfer line exchangers are different in, based on the different licensors, and then the stack and ID fan is still the same actually. So the principal arrangement is mostly the same in all these furnaces. It's showing different services in the convection section. So in the radiant section, that's where heat transfer by radiation is taking place. Almost 80 to 90% of the heat transfer which takes place in the radiation section is by radiant. Say about 10% is by convection. Also, most of the tube failures which occur in cracking furnaces is in the radiant section due to high tube metal temperature, carburization, and all those type of things. So we feel optimum design of radiant section is very, very important. So we'll talk about the radiant section. What should be radiant section doing? We are talking of uniform heat distribution. We want to have no flame impingement, and we want to have complete combustion. Just give me a minute. Let me put the light on. So that's what we are talking of. Now, the thing about ethylene cracking furnaces is it runs so hot that it is almost impossible to see flame impingement. The flames, you really can't even see the flame. So it becomes a big challenge. And we will talk about complete combustion. So that's what we want to talk about. So one important parameter in the radiant section is radiant heat flux density. And it's basically heat duty per unit area. Now in cracking furnaces, what has been happening is, if you see the history of 50 years, how the cracking furnaces have evolved, most of the developments which have taken place due to improvement in the tube metallurgy. The metallurgists have worked very hard, and they have come out with exotic alloys which can allow us to go to almost like 2000 degree F2 metal temperatures or 2100 degree F2 metal temperatures. And as a result, we are talking of very short residence time furnaces. And when we talk of short residence time furnaces, that means we have to heat them in about 0.1 second or maybe 0.2 second, 0.3 second. So as a result, the surface, what we need, the heat transfer surface becomes very small because you want to heat it very fast. And as a result, the flux has gone up from maybe 10 or 12,000 50 years ago to today about 30,000. And when we do that 30,000, that means we are providing only 1/3 the surface area. The radiant section itself, the size has come down. So the furnaces have become very compact. And as a result, the size of furnaces have gone up substantially. That's what has happened. So the limitation is tube metal temperature, coking, and run length. So these are some of the issues with the. All right, so we do have a quiz for you, and this is how much heat is transferred by the radiant section in ethylene furnace. So if I want to tell you, if you look at the refinery furnaces, okay, the correct answer is 38 to 50%. I think the number hovers around 40 to 44%. That's where. If you look at the refinery furnaces, we transfer almost 70% heat in the radiant section. In fact, if you have a air preheater, then the radiant section heat absorption goes up by even another 5%. So the heat transfer could be anywhere around 75%. And the convection section is about 25 to 30%. This is one of the few furnaces where convection section is absorbing more heat than the radiant section. Convection section absorbs almost 50-55% of the heat, as compared to radiation. And that is because of the change that our boxes have become very, very high temperature. So, well, thank you for participating. Let's move on to next one. So, as I said, the radiant section absorbs, I would say, around 45%, and convection section absorbs 55%. And a lot of times you will see the size of convection section is much bigger than the radiant section. The height of the convection sections, you will see, as you can see over here in this sketch, the height of the convection section is much taller than the radiant section. Can happen because we are trying to extract the last BTU or last kilocalorie from the radiant section, from the fuel gases. So let us talk about how does the radiant heat transfer takes place. And if you see, this is the configuration, double row single fired, and all the heaters, when they started building heaters in 1930s, they were built like that, double row. And then they found out that the back row is not able to absorb a lot of heat. In fact, it was only 15%. The front row would absorb 85%, and the back row will absorb only 15%. So they started removing the back row. And most of the furnaces, they graduated from here to here, single row, single fired. That's what they started doing. And then they came to this design, which is double row, double fired. And this is almost similar to the one which I showed you, single fired, but basically still gives you, and it does have a flexibility of adjusting the pitch over here. So that's basically what you see over here. And in fact, there are some furnace vendors, cracking vendors who have started revamping the existing radiation section or existing furnaces with this type of arrangement. That's another reason why I'm trying to show you over here, is to, from this conventional single row, they have gone to double row. So, and they are able to get more capacity or more, out of these coils by going with this design. This is another design which is very, very common. Most of the furnaces are built like that. This is single row double fired. That means tube is fired from both the sides. And what is the benefit of firing it from both the sides is that the firing is very uniform. That means the maximum flux compared to the average flux, that ratio is only 1.2. Whereas if you look at this design, the ratio of maximum flux to average flux is about 1.8. So you can see we can either go for a higher flux in that, or we can go for this design. Now, I do want to tell you that two things have happened. One is everything used to be horizontal. All the tubes used to be horizontal tubes, and I think around 1960s, we started changing from horizontal to vertical. That is another change which has happened in the most of the furnaces, and it happened in the cracking furnaces also. Another change which has happened is in the early days, all these heaters, cracking heaters, used to be side fired. There used to be 6 or 7 rows of burners, and these burners would be called radiant wall burners. The burner flames were impinging on the radiant wall, and from wall it was radiating heat. And that was the common design for almost, I would say, up to 1980s or maybe even 1990s. I think in 1990 they started changing to floor firing. And what they did was they took out the bottom 4 rows and put burners at the bottom. And that's what they did. And I think my guess is 20 years ago, they did away with the side firing completely. And I believe all the vendors are going with the floor burners. Now, there are so many reasons why they did that. I think they found with the side firing, the heat distribution arrangement was not, even though it was supposed to be uniform, but in practice it was not there. The other thing which happened is low NOx burners, ultra low NOx burners, and the third thing is firing of high hydrogen gases. Hydrogen gases are not particularly useful in premix burners. They have a lot more chance of flashback in these burners. So that, I think those were some of the reasons why the industry changed from side wall firing to floor firing. Okay, let's move on. I think I'm running behind time, but that's fine. So this is the configuration: floor firing and sidewall firing. 2 rows of burners on the top and 1 row, two rows at the bottom. And then as I'm showing you, the latest one or the greatest one is burners over here at the floor and coil in the center. That's basically the new current design for the radiant sections, which is being promoted by all the companies. So let's talk about how the heat is transferred in the radiant section. I keep on going to basics, and I will find that the more you understand basics, the better you will appreciate your furnaces. So if you see over here, there are two radiation mechanisms by which the tubes are being heated. One is the direct radiation, and even in direct radiation, there are two. One is the flame radiation, and the second is the flue gas radiation, which basically takes place because of carbon dioxide and water vapors. Those are the molecules which are actually radiating. So those are the two this thing. So the direct radiation, flame and CO2, this thing. And then we have re-radiation. So basically the radiation goes back to the refractory and hits back the back of the tube. So that's basically what is happening. And the next one is convective. As I said, anywhere between 10 to 12% of the heat transfer takes place by convection means. So that's what is happening because the molecule movement of the molecules. Convective heat transfer is associated with movement of flue gases. And once this tube has absorbed radiation and convection heat transfer, now the challenge is conducting that heat from the outside of the tube to the inside of the tube. And that's where I think there are two challenges. We are talking of scaling on the outside, and especially high temperature tubes can scale pretty fast. And the second one is coke on the inside. As you all know that the cracking, no matter how good a cracking you have, you will always get coke formation. So that's another impediment to heat transfer. And once the heat is transferred inside, then by convection, the fluid receives the heat and it gets heated and then the reaction starts. So that's basically how the heat is being transferred in the radiant section. So I'm just trying to show you what I talked to you about. This thing, this is generally the refinery heaters, and this is the cracking heaters. We have burners on both the sides. So we have uniform heating, but it does require double the number of burners as compared to this configuration. So that's basically the double fired arrangement we have. So modern ethylene cracking furnaces are basic. You can either have a twin cell heater, like two radiant sections with a common convection section and ID fan on the top, or you could have two furnaces which are like mirror images, and they are put together. And the reason they are put together is it offers the designers a lot of structural stability. They are able to uh, put a common structure, and then it becomes a lot more stable. That's basically the furnaces are attached. So they are built in pairs, maybe 2, 4, 6, 8. That's typically how, you build the furnace. Lot of furnaces has even SCR systems. They are meant for reducing NOx, selective catalytic reduction system. So they are built into the convection section, and they reduce the NOx emissions in the furnace. All right, we have, I think, so maximum ethylene production requires what? Well, this says all the 4 answers are correct. You need a highly saturated feedstock. That is the first requirement. Then you need low hydrocarbon partial pressure at the outlet. As you see, when you crack ethane and make ethylene plus hydrogen, the volume is going up. And when the volume goes up, it means if you want the reaction to proceed at the fast pace or reaction to complete, you need a low hydrocarbon partial pressure. Very simple, So you need low hydrocarbon partial pressure. High coil outlet temperature, the higher you go, the more ethylene or the product you make. And then again, the short residence time is basically the shorter time you have, the more desirable products you will generate. If you let it give a high residence time, you will have cracking, but you will have other products also coming out. So all the 4 uh, uh, parameters are correct here. So generally, that once you know what capacity furnace you are going to be building, you find out the firebox dimensions, how many radiant coils, how many fireboxes you will have. You could be going with the short versus long residence times, although most of the coils are short residence time these days. A high temperature and low partial pressure. So the way they design the coil, is making all the difference over here. But other than that, the box and the convection section remains more or less the same. There is not much difference. In fact, you people have been retrofitting different coils to get more capacity from the cracking furnaces. So the coil surface area requirement and residence time requirement is selected by the diameter of the coil. and the flux decides how much surface area we need. So it's basically the coil kind of is designed based on these three parameters. Generally, you will see we have, as I said, two radiant sections combined in a mirror image, vertical radiant coils. Most of the radiant sections will have a height of 15 meters or 50 feet. Width is anywhere between 6 to 10 feet. We have burners on the side or on the floor, and they all operate on slight negative pressure. That's typically what we kind of envisage in our designs. So you want to find out what is the outlet temperature you maintain in your cracking furnace. If you have an old cracking furnace, the temperature is going to be lower. If you have a new cracking furnace, the temperature is going to be much higher, So, most of this thing is, I think that's where most of the cracking furnaces operate, around 1450 to 1550. Thank you for your participation. This is a very nice graph drawn by our team, and it shows the coil lengths. Typical coil lengths are anywhere between 100 to 130, 40 feet. That's typically the coil length. And it shows the coil temperatures, the fluid temperatures, process gas temperatures. This is for the naphtha, and the yellow is for ethane, which is another very common feedstock. And we are talking of going all the way up to 840 degree centigrade, which is about 1500 plus 50 or even higher. As I said, maximum allowable flux typically around 27,000 BTU per hour plus foot square, or 85 kilowatt per meter square. Coils are in the center. That's typically how these things are designed. This is a typical design of a cracking heater. Duty is about 75 million kilocalories, 300 million BTUs. Total process duty is around 240. Waste heat recovery is around 62. Radiant section heat duty is around 130. So you can see about 42, 43% is the radiant duty in the radiant section, and rest is in the convection section. So convection section is bigger actually, it's 170 million BTUs, radiant is 130. Firing rate about 315, and the efficiency you can see is almost like 94, 95%, So very, very good efficiency is typical in cracking heaters. This is giving typical parameters. Inlet temperature in the radiant section is around 1050. Flux about 31,000. Maximum flux is 37,000. The ratio between the two is about 1.2. Maximum tube metal temperature is around 1950. Bridge wall temperature, and you can see the bridge wall temperature is the temperature of the flue gas leaving the radiant section, and this is very close, 2150. Volumetric heat release around 8,000. Actually, this looks a lot lower nowadays. They even go to 20,000. Excess air around 12%. So these are the typical parameters of a radiant section for an ethylene cracker. You can see this furnace that has a height of 40 feet, width about 12 feet, length around 30 feet. It has 6 coils per pass, and there are basically 12 burners, So looks like a little smaller heater, but that's typically how the radiant section will be configured, So very briefly, we want to talk to you about a different type of coils. We have three types we have kind of shown over here: single pass, U coil, and a hybrid coil. If you are going for short residence time, then you use tubes of small diameters. If you want to have a medium residence time or high capacity, you use larger tubes. That's basically what. So this is a single pass coil. There is a one, sorry, yeah, there's only one, this thing which comes here, and floor firing is at the bottom. And this is produces highest olefin conversion. This is very similar to what Kellogg had their millisecond furnaces. That's basically the concept over here is uh, the flow is from bottom to top, you know, and that's a single pass. It has the shortest residence time. And the next one is a very convenient one, or sorry, a typical one, which is basically a U coil, and that can have two passes over here, as we are saying, or maybe four passes or six passes, you know, and that's basically the design of the coil over here. You will see the box remains the same. The box is not changing, you know. And these are the more current coils. These are the hybrid coils. As you see, we have the smaller tubes and like six smaller tubes and then joining in one larger tube and going towards the outlet. By having a larger tube, we are able to control the outlet pressure, keep the outlet pressure low, so we get a better this thing. And here we can get the maximum heating taking place. So this is how, you know, and you can see over here. So that's a typical coil design, you know. These are some of the licensors. You must be very familiar with them. ABB Lummus. Actually, it's not ABB Lummus anymore. But they have this short residence time SRT furnaces for last 50 years. Kellogg developed millisecond furnaces. I think they have licensed it to Exxon now and UOP also. And then Technip bought KTI, and then later they bought Stone and Webster. So they have two types of designs, HSC and USC. You know, that's basically the two types. And then Linde has Pyrocrack and Linde Celas combined. You know, so you only have a choice of about 5 licensors, and they cover the whole ethylene industry in the world. This is a design of a SRT5 and SRT6, and you can see over here, you know, the same concept, smaller tubes, and then we have the larger tubes towards the outlet. That's basically the SRT coil. We are able to have a residence time anywhere between 0.15 to 0.2 seconds. Similarly, we have a Linde Pyrocrack, and here also we have this multiple coils coming and then combining into this thing. Here we have 4, 2, 1, this is 2, 2, and this is 1, 1, you know. So these are different coil configurations to limit the residence time in your furnace and get the required yield of ethylene. So when we talk about radiant heat flux, these are the typical numbers. For ethane, we use 23 to 27. Propane also same. Naphtha, we can go up to 30,000, or gas oil cracking even higher, so 26 to 32,000. All right, let's have a quiz, you know. So so you will see Actually, none of the answers is wrong, you know. I mean, depending on if you had an old furnace, your crossover temperature may be lower. If you have a new furnace, your crossover temperature is going to be higher. So I apologize. I think this should have been more like a poll instead of a single correct answer. But what we want to show you is in the last 25 years, they have been trying to preheat the feed in the convection section to a very high temperature. And that basically reduces the heat requirement and uh, also reduces the residence time in the radiant section. If the feed is already heated to 1250, I just need to heat it up to about 1500 or 1550, you know, so then I don't have to do too much heating, you know, sensible heating. Well, thank you for participating. So you can see over here. Okay, just give me a break. Oh, yeah. We have a energy conservation in our offices. So if you don't move, the light goes off, you know. So as I said, crossover temperature, we're talking of ethane cracking, propane cracking, naphtha is much lower, gas oil is even lower, heavy oil is even lower. So you can see how it is increasing as the feed becomes lighter, you know, limited by the feed. And the reason is because if you heat it even further, then it will start coking, you know. So, okay, as we talked about that the furnace is going to be coking, you know. So what is the typical temperature rise in your furnaces? Uh, these numbers are again, this was again a poll, you know. I think we should have fixed it. But anyway, this is 1 to 5 degrees, the best furnace if you have 1 to 5 degrees. If you have 4 to 10 degrees, then you are having, you know, or 8 to this thing, you will have a much faster coking, you know. So these are the typical temperature rise. If you have a cracking furnace, you will be increasing the temperature 1 to 2. If you have as the feed becomes heavier, the coking rate keeps on going up. So you can see typically up to about 8 degrees heavy oil, you know. So that basically determines the run length of your furnace. I mean, if you have got 1 to 2 degrees, then maybe you can run all the way up to 100 days or even 120 days. But if you have 3 to 5, you can run only 45, 50 days. So that's basically how your run length will be taken care. So one thing I want to introduce, and what we have been doing is most of the time when we talk of coking, we are only talking of coking from the coil side. But we all know that it is the flue gas side which also contributes to coking. And what we have been finding is that these are the 4 important parameters which can help you reduce the coking, or if not taken care properly, will accelerate the coking, you know. And the 4 parameters we want to talk about start with the burner heat release per burner, how big your burner is, then the clearance between the burner to tube, and the burner to burner spacing, how your burners are spaced, and then the burner air side pressure drop. And we'll talk about these. We think these are the 4 parameters. If you focus on these, you will be able to reduce the coking in your cracking furnaces. So let's start with the first one, heat release per burner. All we want to tell you is that if you use a larger burner, you will have more coking. If you use smaller burners, you will have less coking. That's basically this thing. Yeah. And you can see over here, if you have shorter flames, we will have more uniform. The whole concept is based on uniform heat transfer. The next is burner to tube clearance. This is very, very critical. We have found that flames, when we do CFD modeling, flames tend to lean towards the radiant tubes because they are at a lower temperature. So flames are looking for low temperature, so they tend to lean. And the greater the distance, more uniform heating will take place. What has happened in the industry is in the last 20-25 years, we have started resorting to low NOx burners, and low NOx burners, as you know, have a very long flame length, almost 2 to 2.5 times the flame length, and that increases the chances of flame impingement. So if you can keep your flames away from the tubes, that will be the best. And as I said in the beginning, since it's such a high temperature furnace that once it starts running, you cannot see any flame because the bridge wall temperature or the firebox temperature is more than 2000 degrees F. So it's virtually impossible to see the flame. So you can only, see it during startup or when it is running cold. Another important parameter we found is the burner to burner spacing. We think the more burners you have, the better uniform heat transfer distribution you will have, because more burners means shorter flame lengths and uniform heat transfer across the whole length of the heater. So see if you can think of, if there is a possibility of installing more burners in your furnace, that will definitely help in improving the flame patterns. All these things are based on the flame patterns, and these are all practical things. So burner air side pressure drop, that's another, if you look at the burner and if you look at the flame, we are using two sources of energy for mixing and generating a flame. We have fuel gas pressure, and then we have the combustion air or the draft gas. Fuel gas pressure, typically we use 25 psi, and air pressure is very, very important, and especially because the volume of air is anywhere between 15 to 20 times the volume of the fuel gas. So the higher the draft class, the tighter will be the flame. If you use forced draft burners where we have 2 inches or 3 inches of air pressure, then you will have even tighter flames and you will have much better combustion. So these are the 4 parameters I talked about. Nobody talks about coking. In fact, the burners don't never figure in radiant heat transfer calculations. That's the situation, that there is no parameters. And you will see, I think I will cover it, that all heaters are still designed based on 1940s Lobo-Evans correlations, So the number of burners or these things do not come into the picture, So I just want to give you a little brief about our inclined firing technology. Our inclined firing technology is very simple. It is based on diverting the flames away from the tubes. And our CFD group did this modeling of a small cracking furnace. And what we have seen is, if you do it, we are able to lower the temperature by 50 degrees to 100 degrees in cracking heaters. And you can see the CFD model over here. There are 2 rows of burners with a tube in the center, So this is typical configuration of a conventional vertical cylindrical firing, vertical firing of upfront firing. And here what we had done is we have put the burners at an angle of about 7 degrees, and we are trying to fire it across the wall, around the wall, And I just want to show you a few of these things. So you can see the difference, You see the flow gas temperature contours are closing towards the tube, Whereas when I do the inclined firing, those red zones kind of get disappeared. Now this is looking at the flame length. You can see the flames are so close to the tubes over here, and here they are very much away. The flame length does go up, but it does give you a much better uniform heat transfer. You see, the beauty of the radiant section is the radiant section does not need a medium. If you are looking at radiation, we are able to receive heat from the sun even though it is millions of miles away from us, So it does not need a medium. Similarly, you don't need to keep the flames closer to the tubes. The flames can be as far away from the tubes and you will still receive the heat transfer. In fact, you will receive the better heat. The farther the flames are, the better heat transfer you will have, So that's the basic concept, Keep the flames away from the tube. Very simple concept. It can be done using your existing burners that you don't even have to change the burners, This is again showing the mole fractions over here. How, mole fraction is CO is 2000 ppm of CO is considered a flame. And you can see over here, the flames are almost touching the tube, high temperature. Whereas when we put the inclined firing, we are able to get flames more towards the wall, and this is all clear, And you can see almost 90-degree reduction in the tube metal temperature, So I think it has a place. If you are having any issues on high tube metal temperatures, you can talk to us and we will be able to see whether your furnace is a good candidate for inclined firing, whether it can, really reduce the tube metal temperatures. All right, that's all I had. Here is an open question. What is the maximum tube metal temperature of ethylene cracking heaters? You can type your answer. Okay, show answers. Let's see. I think these could be centigrade actually. That's what I'm kind of thinking, 15 to 1600 degree looks low, but 2000 degrees, 1950, they look right. Well, thank you for participating and providing these numbers. We have another quiz coming up, multiple select. What are the key elements in selection of right metallurgy for cracking furnaces? Okay, this should be pretty simple. Well, most of you got it right, all of above, Cost, run length, tube metal temperature. Thank you. Give me a feedback if you like these quizzes, we want to see, whether this effort is worth it or we can go back to our normal PowerPoint presentation. Your feedback is important because this webinar is for you. So we just want to get your feedback if you have any suggestions. Metallurgy selection, coil metallurgy. Nowadays, we are going anywhere between 35 nickel, 25 chrome. The factors which affect the coil material are operating temperature, tube service life, cost, carburization resistance, creep rupture strength. So all these factors basically uh, affect the coil metallurgy, what you select. But I think the good news is we have coils which can go up to, this is 1830, but we can go even higher. And as I said, localized overheating must be avoided, and that's where the flames can help you out. Improving the flame patterns will really help you out. Radiant coil generally in other heaters is only 10 to 15%. Here it is 33% of the furnace capital cost. And it only lasts 5 to 7 years, does not. Generally we talk about 100,000 hours, which is about 12 years for most of the other furnaces, but here we're talking of only 5 to 7 hours. And the reason is because of carburization, the tubes can, give way and we'll have to change the tubes. Well, these are some of the metallurgies which are used. HK40 has been there for ages, almost 30 years, or maybe more, I should say 50 years. HP low carbon, we from HK40 when we get to HP, we increased it by 100 degrees. Then we went to HP microalloys, we increased it by another 100 degrees. Then we went to HP modified, which is pretty the same, and then 35 chrome, 45 nickel, we can go up to about 2100 degrees. And this may not be the end, actually. You may still be getting more. I don't know whether our metallurgist can come up with an alloy, and that's really good, actually. It has been a big improvement, the coil metallurgy. And besides this, there are a lot of other things. The vendors are coming out. They are coming out with mud. They are coming out with coatings. They say if you have aluminum coating, it kind of repels carbon, so you can, do that also. So there are lots of technical things which are taking place. Next, we want to talk about transfer line exchangers. They are important because you want to cool the product from the heater very, very quickly so that you don't have any undesired reductions. So that is done in transfer line exchangers in very, very quickly. And as you can see here also, the residence time is very, very fast, that in you cool it down, very, very fast. In five milliseconds, you cool it down. So you can avoid, Well, let's move on to convection section. As we have said, radiant efficiency is only around 40-45%, out of which 30% is used in the reaction and 12% is used in the approximately in the process preheating. And then these flue gases leave the radiant section, enters into convection section. And in convection section, we are talking of preheating the process, and which again is about 35%. And then 16% is used in high pressure steam generation, high pressure steam superheater. So that's, and then the stack losses are only about 5%. That's what we are kind of, Convection sections have typically been the same. No matter whose furnace you are going, you will always have a horizontal box. It will be slightly offset. That's generally the design, and these are the different services we have in the convection sections. This is showing a crossover, from the radiant section to convection section. And a lot of times this area generates or radiates so much heat that you can even start getting coking or tube overheating in this bottom area because of the lot of high temperature flue gas volume. So it kind of accumulates the radiation and starts going into the shield tube. So you need to kind of calculate and make sure. Also, even though we are showing it like this, in reality, it may not be that uniform, depending on the design. So that also needs to be taken into consideration. So what are we trying to do in convection section? We are trying to recover the heat, and that is for minimizing energy cost. So we want to recover the heat, and that heat is used for preheating the liquid feedstock, or if you have a gaseous feedstock, then we preheat the gas feedstock. For preheat boiler feed waters, generate superheat steam. Then also we preheat dilution steam, and then preheat the dilution steam plus hydrocarbon mixture. That's typically what we do in the convection section. Convection section generally will have two sections. We'll have a shield or shock section, and the second one will be extended surface sections, which are fins or studs. And the basic equation, just like any heat exchanger, is UA LMTD. So convection section design is much simpler. It's almost like a fin fan cooler, And I'm just giving you an equation which is for calculating heat transfer coefficient. And as you will see, there are two parameters I want to talk about. One is the flue gas mass velocity, and the other is the tube OD. And you will see the higher the velocity, the higher the mass velocity, the more heat you will get transferred. And the second is the tube diameter. The lower the tube diameter, better heat transfer you will have. So if you can use 3-inch tubes as compared to 4-inch tubes or 6-inch tubes, you will get better heat transfer. And one thing which I forgot but might have told you is whether it is the radiation section or the convection section, all the heat transfer in these furnaces is controlled by the flue gas. Whether it is a radiation, convection, the heat transfer is controlled by the flue gas. So even though we call it a convection section, but the flue gas temperatures are very, very high. So we have a substantial amount of radiation taking place in these furnaces. The radiation is because of the presence of hot flue gases. It's also because of the presence of hot flue gases between the tubes and then from the convection walls. And I told you about the mass of the hot flue gas before in the crossover, And generally, they will use bare tubes unless the flue gas is cooled down to about 14 to 1600 degrees. That's generally the design, this thing. So the question is, why use fins? Why do we use fins, So as I just a moment ago said, the heat transfer is controlled by the flue gas. So if you're talking of any fluid, the inside heat transfer coefficient could be anywhere between 100 to 200 or even 300, And the outside heat transfer coefficient is generally of the order of between 5 to 8 or 5 to 10. So as a result, it's the outside heat transfer coefficient which is controlling the heat transfer. Or anytime that happens, we can provide more surface on the outside and control the or improve the heat transfer. And that is the one biggest change which has taken place in the last 50 or 60 years is use of finned heat transfer. When we fin the tubes, we are able to increase the outside surface area almost 10 to 12 times. And by doing so, we are able to replace 3 bare tubes or even 4 bare tubes with one tube, one fin tube. That is how effective finning is. And as a result, the convection sections have become very compact. They have become much economical because they can be fabricated in shops and then they can be shipped in modules. So finning really helps in heat transfer. And that is because the heat transfer is controlled by the flue gas side. So this is sketches showing you the different components of a convection section. We normally have casing on the outside, and we have intermediate tube sheets. You can see over here, 2 end tube sheets by which the tubes are supported. Then we have these header boxes where the return bends are housed. We have refractory lining on all the sides for insulating the casing. And that's basically it, the convection section. This is showing you the intermediate tube sheets. The horizontal tubes require tube supports every 35 diameters. And because of that, you put these intermediate tube sheets. These are of high chrome nickel because they are experiencing high tube metal temperatures or high, And then you can see the header boxes, you can see the inlets, you can see the return bends. This bottom are bare tubes, then you can see the fin tubes and the provision for future rows. So those are all these common things. So some of the things which is available is, the feed is available at low temperatures. Actually the feed, if it's a gas feed, it's available at as low as 150. So we preheat it and then we mix it with steam and heat it all the way up to 1100 or 1200. And the flue gas from the radiation section is almost is as hot as 1100 to 1150 degrees centigrade. And we can cool the flue gases to anywhere around 110 to 150 degrees centigrade. Approach between flue gas and fluid can be done like 15 degrees centigrade or 25 degree F. What we are preheating is feed preheat, combustion air preheat, or boiler feed water preheat. Those are the things we are preheating in the cold end. But you can see how monstrous the convection section is, actually, how big the convection section is. This shows you the flue gas temperature profile and the fluid temperature profile. This is where the flue gases are entering the convection section at about 2100 degree F. And then slowly we are cooling it down all the way to 253. And we have first one is lower mix preheat. Then we have dilution steam superheater. We have a lower HP steam superheater. Again, another middle HP steam superheater. Then we have a mixed feed preheat. Then again, HP steam superheater. You can see that. And then finally the boiler feed water preheat and mixed preheat. over here. So we have been able to extract the last, you can see it's only about 70 degree. And most of the heating is co-current except these two which are counter current, but most of the heating is co-current, and you can see over here. This is a coil arrangement, a typical coil arrangement in because of gas preheating. Yeah, I still have a few minutes. So this is for the gas feedstock, a typical this thing. This is for a liquid. The only difference is you vaporize the liquid, so you had to give another this thing. And we said just like that, this is the flue gas temperature profile for the same heater. What are the issues in convection section? Some of the issues are non-uniform flue gas distribution, even though it's not very common. Convection section fouling is pretty common, and lower crossover temperature is even more common. I mean, a lot of times those convection coils don't behave as they should have, and that could be a shortcoming in the design. And as a result, the crossover temperature is not what they were supposed to be designed, so you end up firing it harder actually. So we still have a few minutes left. Let's talk about the furnace draft. There are two types of draft we utilize in these furnaces, natural draft and induced draft. And in the old days, the convection sections used to be small, and we would design them with lower flue gas mass velocity, so we could have natural draft furnaces. But not anymore. I mean, now we have large convection sections, and the convection sections can have anywhere between 30 to 50 tube rows. That's how deep the convection sections are built. The pressure drop across the convection sections could be anywhere between 3 to 5 inches of water column. And if you have an SCR, then you can add another 1 or 2 inches or 3 inches of pressure drop. So there is no way the stack can provide that type of draft. So you end up using an ID fan, induced draft fan. This is another one installation, and this is another installation with two fans, So that's what you end up using it. One thing we want to talk about is draft control, because everybody talks of O2 control, and that is only half the story. When you talk about O2 control, I mean, everybody, all the people who are in operations, they talk about what O2 you are maintaining, but nobody talks of the draft, because draft is equally important as excess O2. Anytime you make a change, you are make a change to one parameter, the second parameter automatically gets affected. The good news is that the oxygen analyzers have improved substantially. There is a big improvement in oxygen analyzers, so we have very reliable oxygen analyzers. The heaters are not pressure-tight structures. Air can leak from different openings if there are any openings, peep doors, expansion joints, penetration seals. And this O2, which is leaking, is called tramp air. It does not take part in combustion. It shows up in the oxygen analyzers, and it kind of messes your O2 control. So our effort should be all the O2 which is going into the furnace should be coming from this thing. And this kind of shows you a draft profile. You can see how much. This is at the burners, this is at the arch, all negative, and then these are all the pressure drop in the convection section. And then we have an ID fan which provides a required draft, and then it sends it to the stack. This is a simple guideline based on ID fan damper and burner register. If your O2 is high and draft is high, close the ID fan damper. Or if your O2 is high, draft is low, close the burner register. So it's a very simple guideline for you. So thank you very much for giving me a patient hearing. We just want a little bit of feedback from you. If you can give it to us. Did this webinar meet your goals? Well, thank you. Was the course content clear and easy to understand? Thank you. And I think the last one is over here. Thank you. I think I need improvement, honestly. I'm trying, actually. I was trying to rehearse on PowerPoint, and it gave me a very good feedback. It said you need a lot of improvement. Well, thank you very much. We hope we will be able to see you again. Let's see if there are any questions here. Oh, I hope all of you were able to hear me, because one of them is saying the volume stopped working. So if that was the case, I really apologize. So thank you all.